Good morning everyone. Welcome back to online classes of VLSI Design. In last class we have seen about your CMOS inverter as well as the BiCMOS inverter. I hope you have gone through the video completely, and I also expect that people are not having any doubts regarding that topic. In case of any doubts, please do let me know, and I have given the links of the previous classes also over there. Okay, go through the links because first chapter of VLSI is very important. Okay, so be prepared, prepare well. I don't know whether IT students are saying that they are having internal exams. I'll just give the questions also, important questions for you people. So today in today's class we are going to see our next unit, that is your VLSI circuit design process. So in first chapter we have seen completely about your fabrication process. First we have seen the generations of ICs, right? We are having different types or different generations. I have already said, like SSI, LSI, MSI, VLSI. Okay, so we have seen all the different generations. We have seen how fabrication process is going on, how we are going to fabricate an IC. Then we have seen what are the technologies that we'll be using, what are the steps we have seen. Okay, then we have also gone through the mathematical part in the part B of your first unit, that is basic electrical properties of your MOS and BiCMOS circuits. In that we are having very importantly drain to source current characteristics, that is IDS versus VDS. Okay, so there are the important topics. First chapter completely having all the important topics, so we can expect long answers from that one as well as the short answers. For sure you'll be getting at least 25 marks from that. So you prepare first unit very thoroughly. It is very important. In the second unit what we are starting today, it is also very important. Here we are having the VLSI circuit design flow, how we are going to design a chip, how we are going to design a circuit, that will be seen. So for that one, what are the important steps we are having, we'll see in that one. Okay, so first see what is VLSI circuit design process. So this to design a particular chip, what are the requirements you need, that we are going to see in today's class. Okay, in this complete chapter. So VLSI design flow, what is actually an VLSI design flow, what you are going to do in that one. So a design flow is a sequence of operations that transforms the IC designer's intentions into a layout of GDSII data. That is your VLSI design flow. So as I have said, what is VLSI design flow? Design flow means you already know, as if a flow chart. What you are doing in that one, it is sequence of operations. Whatever the operations you are going to perform, that you have to transform. Your IC designer is transforming his intentions into a particular layout. In which kind of layout he is transforming? It is nothing but in geometrical database standard for information interchange. So we have to interchange. Why we are actually preparing an IC? For different kinds of applications. IC I'll be using in laptops, IC I'll be using in my phones, IC is used in different all electronic components. So it is a part that you have to interchange your information. So it is having some geometrical database standard for information interchange. So your design flow is a sequence of operations that transforms the IC designer's intentions. My intention was to prepare some washing machine. So in which it should automatically steam up the clothes, or it should dry the clothes, and it should do all different operations, okay, for soft clothing and different. So we have prepared an IC. These all intentions, whatever the intentions I have that I have dumped onto that IC, and that has to be into a layout format of GDSII. That is nothing but your geometrical database standard for information interchange. Whatever the information I will be giving to that particular washing machine, that has to be operated, that IC has to be operated. So your VLSI design flow should be in that manner, that it should be having some information interchange with some database standards. So this is a particular small definition or a brief explanation of about your VLSI design flow, what you are going to do. Next, a well-tuned design flow can help the designers to go through the chip creation process relatively smoothly with a decent chance of error-free implementation. See what actually we are doing. If you are having a proper design flow, you say that if you are having so and so steps, if you are having properly, then if you are creating a chip, there is a smooth flow of chip. If you are not proper in your data chart or a data flow, then there is a compulsory error in that implementation. So if you I'll give a small example so that everyone will remember that one. Like if you are preparing some recipe, correct? So what are the ingredients we are having? We'll keep a list, but the steps what you have to do, which one has to be gone to the bowl first, that is much more important. Yes or no? If you are not having any proper idea, proper steps in that one, obviously your recipe will be full of errors, we can say that one, right? So it is also type of something. So if you are having a design flow, well-tuned design flow, step-by-step design flow, if you are having, that can help your designer to make a proper chip which will be having error-free implementation, right ma'am? And a skillful IC implementation engineer, the engineer who is preparing this IC, can use the design flow creatively to shorten the design circle, resulting in higher likelihood that provide the product with the catch the market window. What it actually means that, see, whatever the design engineers will be different and implementation engineers, that will be different. So if the design is good and proper enough without any errors, the implementation engineer can use that particular design flow to create a chip which is small in size, which will be shortening in size, plus its design cycle also will be shortened, resulting in your higher likelihood. Means it should attract the customers in such a way that it will be getting good rate at your market window. It should catch the good attraction in your market window. So you have so that's the reason design flow is very, very important. How we are selecting the chips. So if you are designing something, a chip you are designing for your laptop, you have to see how many transistors that has been used, how much memory you are going to use in that one. Inbuilt you have to see, no, on that one. So the design flow, how much floor planning will be there, what is the chip size will be there. If you give this design flow clearly to the designer, he'll make an IC with all this reliability and makes attracted to the market so that it will be purchased very easy. So design flow is the sequence of operations that transforms the IC designer's intentions into a proper layout. Which kind of layout, ma? GDSII data layout. Fine. So I hope you are clear with the introduction part of your design process. Correct? We'll just move to the next part. We have given here algorithm or the flow chart or layout of your VLSI design flow. It consists of different steps. After this also we are having 2 more steps. Do listen carefully in the last. I'll give that one. Okay. In my notes also you are having. I'll send the notes also to you people. Fine. So very first one, we are starting with the design entry. First I'll tell all the components. Then we'll discuss one by one. Fine. So first one is design entry. For very first we have to do the specifications here in the starting itself. We have to do all the specification. What you have to keep what all the components you are using and all to your designer. Then next you are having the design entry. Okay, to enter all the designs. Then you are having the logic synthesis. Then you are having the partitioning part. So these are all your front end parts. All these 4 blocks, whatever you are having, 1, 2, 3, 4, this part is your front end part, and from here, from 5th to 9th, this is your back end part. So this your system is divided into 2 parts, specification. First part is your front end. Up to this step, you are having, this is your front end part, and this part is your back end part. So in the back end part, what you are having? You are having the floor planning, then you are having the placement, okay, then you are having routing, then circuit extraction, and again post layout simulation. Your pre-layout simulation you are having here, and you are having the post layout simulation. Okay, let's just see it step by step. Very first I have said in the start what you will be having, a design specification you will be having there. What is meant by design specification? Means you are specifying, or your specification allows each engineer to understand the entire design and also helps the engineer to understand the entire the entire rest of the circuit. Suppose in the starting itself, in the specification, I'll say that I want to prepare an IC for your mobile phones. Okay, so if you are using for mobile phones, what are the what you all need? You might be needing a camera phone, like a camera, memory, for sounds, videos. Okay, for all this you need something. So the designer gets an idea that okay, so and so I have to prepare. Okay, that is nothing but specification. You are specifying the particular application what you are going to prepare. So if for the designer, it will be getting an idea what all kinds I have to prepare. Correct? Now next. Well, next what you are having. So see, very important, because why we are going the specifications, because it will be reducing the time for the designer that I got this so and so specifications, how I have to prepare, what are the different things, how I have to prepare the block diagram of that particular one, how timing specifications I should give, what is the package I have to require, how many number of gates I will be requiring, how I have to dump that gates, where I have to dump that gates, how much power consumption will be used, and what are the procedures, what are the different tests I have to do. In the starting itself, he'll declare all these things, and very importantly, what is the total cost of the target design. Okay, he'll be seeing all this one, where in the start, here in the start itself, you will be having a design specification block also. It has gone here. So here in the target specification, design specification, so all this will be included. Okay, now second one is your design entry. Now here you are going to design. Okay, why you are going to use the design? Because it is used to enter a design with a schematic editor or by another test based software tool like HDL or VHDL or Verilog. Okay, either HDL, VHDL or Verilog. Here we will be having two schematics, either here, as I've said, schematic entry or HDL entry. Okay, so for first part, specification we have given that we are going to prepare so and so, the designer, so the designer will be having all his ideas, like what will be the block diagram and all. Then afterward you are having the design entry. Design entry is nothing but you are going to write a program in the editor. Either it may be software, completely depend upon the tools what you are having. The software tools basically that are used in your VLSI is your VHDL or Verilog. See, first part is here. Okay, this is the design entry, right? Now tell me, what is your schematic entry? As I've said, we are having two entries. First one is schematic entry and second one is your HDL, VHDL entry. In schematic entry, it completely provides a graphical interface. Okay, you are building your complete system with individual gates or by combining the gates and creating a functional blocks. So all this graphical representation or the graphical interface is all in your schematic entry. Okay, where comes to your HDL entry, this entry is what you will say, it supports mixed level description where gates and nest list constructs both are used in the functional description. Okay, I'll repeat it once again. What you are doing, design entry, we are having two types. One is schematic entry, where you will be having complete like graphical representation. In a HDL entry, it is a combination of your what we will say, graphical also type of gates you will be asking, plus the net list. What is the net list? All the data, what is how much it is required, what are the things that are required, how many gates are required. That completely it is a combination of your gates and net list which constructs both and along with the functional descriptions. Okay, then next you will be having your logic synthesis. Now what is meant by logic synthesis? This tool is used to produce the complete net list. It means the logic cells and the interconnections which are used in that one to prepare an IC are described in detail in this net list. Fine, ma'am. So what actually this logic synthesis will be doing? This tool is used to produce the complete net list. Here, see. First design, in specification you have given so and so specification. Design entry you are giving the VHDL or Verilog tool. Okay, whatever the tool you are using over here. In synthesis you will be getting the net list. What is netlist? It gives a complete description of your logic cells and the interconnection that you are going to use in that particular IC clearly. Okay, in detail it will be giving you a list. Okay, then third one, you are having the system partitioning. What is my system partitioning? It is a process of dividing a large and complex system into smaller modules. Okay, we will be using your IC for different modules. One IC is not completely addicted or completely given for only one module, right? So we'll be having different modules for that one. As I've said, given an example that we are going to prepare an IC for your mobile phones. So it is not just used for receiving the calls or dropping the calls. No. We will be using for texting also, for video calls also, for listening music also, for capturing the cameras, for capturing the pictures and all. So all these are different modules. So you're partitioning, you're dividing this larger system, your complex system, into the smaller modules, different modules it will be done. Then afterwards, then it is given to your pre-layout simulation here. What is pre-layout simulation? Why it is required? Because it is required for verification of the circuit design through software programs. First only we'll once verify whatever the design what we are using is proper, either here HDL or schematic, or then we will be using the logic synthesis, all the interconnection and all the components that we have used are correct, and partitioning. We have taken some 10 to 20 resistors or 10 to 20 transistors. They each are given for particular modules. Here partitionized, no? We have to check whether they are given equally or not. Then we have to give it for the pre-layout simulation. If it is okay, well and good, then it will be going on. In case of you are having any error in the design entry or in the logic synthesis or in the partitioning, again they will be rectifying and they will be going for the second part. That is your backend part. This is your front end part. Now you are going for the backend part where you will be having the floor planning. In the next slides, I have given one by one the theory also. First, we will discuss in the flowchart itself. Fine now? So, floor planning. So, what is the floor planning? The main function of this floor plan is to estimate the required chip area that will be used for each standard cell or each standard module what we have designed, what we are going to design. Here, up to here, you are clear. Your system partitioning, correct? What is partitioning? As I have said, we'll keep in the mind that we are going to prepare an IC for your mobile phone. I am having 5 modules. I am partitioning this complete system into 5 modules. What are that 5 modules? One is for camera, one is for texting, one is for calling, one is for video calling, and one is for capturing the pictures. Okay, 5 different modules, any 5 modules. So I have to see that in the floor planning, I have to estimate the required chip area. Whatever the modules you are going to use, what are the cells you are going to design in that one, that particular area is available, or I have to prepare that particular area. I have to see in this one, in floor planning. So for every particular chip, how much, this is the first module area, this is second module area, this is third module area, this is fourth module area, this is fifth module area. So this is how you have to check whether you have to estimate the required chip area. Okay, we are estimating over here. Then after that, we are having the placement and routing. These 2 parts we are having. What is placement? We have to place the blocks. We have said that this part I will be using for your we have given an example of 5 modules you are preparing. Here in this part I will be using this part for preparing a camera, okay, for capturing the pictures. Here I will be using some memory allocation. Here I will be using the particular module as to record the videos or the video calling. These particular parts I will be using for the texting purpose. This all is there, but which components has to be placed? That are done by using your placement. Here all the blocks has to be placed. Okay, so all the logic blocks which are assigned in some specific location on your particular die are to be properly placed, and that placement is done in your 6th part. After floor planning, we have given all like if an apartment, we have given 5 to 6 floors. In every floor, how many rooms and how many like whatever the furniture and all arrangements we have to do, we have to see, we have to place them properly in the 6th block. Then afterwards, routing. What is by routing? Routing is nothing but interconnecting. You have placed everything. You have placed transistors, you have placed resistors, you have placed all your memory blocks, whatever you have placed, they have to be interconnected in the proper way. So this part is used for your routing, nothing but your interconnection. So the logic blocks which are assigned particularly, that has to be interconnected. They have to be interconnection elements on the particular die. Die is nothing but your IC what you are going to prepare. Okay, ma? I'll repeat once again these two steps. All the logic blocks which are assigned with some specific locations on the die, they have to be placed, and at the routing stage or the root stage, the logic blocks which are assigned particularly, they have to be interconnecting the elements on that particular die. Okay, I hope you are clear with all these 7 parts, 7 blocks. Now we are having the circuit extraction. Okay, we have placed, we have given the spaces, we have placed all the elements or the whatever you require the blocks, and we have given the routings, okay, all the connections, then we have given it to the circuit extraction. So these extraction or these process determines the resistance and capacitance of all the interconnections. You have to see in which circuit you require a resistance or the capacitance value, where it has to be loaded, or where you have to go for the unloading process of your voltage, then how much resistance you will be requiring. Okay, you have to resist some current also, no? You can't give whole current at a time to your every block. So all this in circuit extraction, what you are going to do, you are determining the resistance and the capacitance for all the interconnections you have done. Up to here you have done routing. Everyone is interconnected. You have interconnected all logic gates, resistors, capacitors, transistors, everything. But each and everywhere you require some capacitance and you require some resistance. So this part will be done in your circuit extractions. Fine. Then it is given to the post layout simulation. Pre-layout, we have seen how we are going to design, what are the steps, or all the what are the steps we are going to see that one. Okay, pre-layout for verification of the complete circuit. Okay, then next we have only in the software program. Now this is your hardware part, backend part, right? So in this what you will say post layout simulation, after this all physical placing and routing, this simulation is carried out. We are doing after all this placing and routing and giving the proper circuit extraction, capacitors and resistance, then we are carrying this step. Which step? Post layout simulation. So in post layout simulation, if the result is good, then the designer proceeds for chip finishing part. Okay, design it. So after, if the post layout simulation is okay or it is good enough, then only your designer will proceed the chip for the finishing part. Here it comes. In case if you are having any doubt in the floor planning, if the place is not proper or the placements of cell is not good, it is not done, or routing or connections is not proper. After routing also, if you are not giving the proper resistance and capacitance value, again this process, this backend process will be done. If it is okay, if your result of this post layout simulation is good after compiling, then your designer will be finishing the process or finishing the chip part. Okay, so after physical placing and routing, if the simulation is carried out, if the post layout simulation result is good, then only the designer proceeds for chip finishing part. Okay, I hope you are clear, right? So next, after this you will be having 2 more steps now. It's not here in this one. You will be having the physical verification. After preparing all this, once physical verification part will also be done. Okay, after placement of all this, routing and all, full custom editing physical verification will also be carried out. And that verification will be based on our design rules, whatever the design you have done, and you will be seeing the electrical rule check. Okay, DRC, ERC will be saying that one. They also check that one. Then antenna check, if you are using for any communication purpose your ICs, then your antenna check will also be. Short circuit check will also be done. In case of current, if you are having any short circuit, so physical verification will also be done after finishing of your chip. After this part, you will be having one more verification, that is physical verification, and testing is also be done before production. If you are going to prepare some 100 chips, before that one only, first chip will be tested. If it is good enough, it is giving the good results, then it will be moving for the next part. Or else again we have to do all these steps. And lastly, you are going to do the chip fabrication. Okay, before submitting it to the designer, then you are going to chip fabrication. You are seeing that all the input output pads are placed correctly, you are getting the outputs properly, then it is going for the marketplace. So this is how you will be seeing your, which one, the design rule of your VLSI process or the chip process. Okay, how we are completely designing. What you are going to design now? Your chip, nothing but your or IC, how it is going to VLSI design flow, your IC design flow. Correct. Here I have given the proper step by step. See, in the front end part you are having this logic design. Correct. Not all logical synthesis. In the back end part you are having the physical design. Correct. This is it. From here you will be having physical design, placing, routing, blocking, and circuit extraction. This is your front end part. Once we will revise all the steps here clearly. In the front end part, in the logic design, the first one you are having design entry. As I've already said, enter the design in the ASIC design system using a hardware description language or a schematic entry. Right? Then you are having the logic synthesis, where the generation of netlist. What is netlist? It consists of logic cells and their interconnections. How many blocks you are going to use, what are the logic cells, and how connections will be done, that all will be seen in your netlist of your HDL code. Next you will be having your logic synthesis will be consisting of few steps, that is like technology independent logic optimization, then translation like behavioral model to the structural design, then technology mapping or the library binding. So these are all your logic synthesis. Then after logic synthesis you will be having the system partition. What is system partitioning? Dividing a large system into a ASIC sized pieces. Then next, in the last part of your logic design or the front end design, here after system partitioning you are having pre-layout simulation. What is pre-layout simulation? Check to see if the design functions correctly or not. Correct? So gate level functionality and timing details that are all verified in your pre-layout design. This all is your logical design part, that is your front end part. Now when it comes to your back end part, what you are having here? Floor planning. First one, as I said, floor planning. Then you will be having the placement, then you are routing, then circuit extraction and post layout simulation. So what is floor planning first? Arrange the blocks in the nest list on the chip. Means whatever, what is the net list I have already said here? Logic cells and their connections will be given properly. Here by seeing the figure also you can get to know that one. Okay. So floor planning gives you complete information like how we are going to use that blocks, what are the interconnection, where we are going to use that. Then afterwards placement, decide the locations of that cells or the blocks. Okay. Then you will be having the routing part, making the connections between the cells and the blocks. Okay. Then circuit extraction to determine the resistance and capacitance of the interconnections. Then lastly you are having the post layout simulation to check or to see the design still works with the added loads or not. In case of any doubt or if it is not the result of your post layout simulation is not good enough, again you have to go back to the first part, that is not that first part. Here in the back end parts, physical design first part, that is your floor planning. Again go back to the floor planning, see the placements of your cells and blocks is correct. Routing is also correct, nothing but your connections between your cells and the blocks is correct and not. Then we have to go do the extractions, that is give the proper resistance and capacitance for your interconnections. Again go for the post layout, then see whether it is well and good. If you are getting the good result of that one, then you will be getting the output. Then you will go for 2-3 steps. What are the physical verification it will be done. Okay, for doing electrical shocks and something you will be going on. Then after that one, after testing, physical verification, you will test once, that is the chip is properly working in all terms. Like if I say if the chip may be failed because of some electrical or mechanical problems, or it may slow down the complete circuit. We have prepared the chip completely, but at last when you are going to using in that particular application, it may slow down the process, or due to some electricity problem or some mechanical problems, it may slow down the system. So we have to test that one. First we have to physically verify, then you have to check, Then afterwards it is well and good. Then you are going for the chip fabrication. Now that chip has to be fabricated in your particular application. So this is how your VLSI design flow is on. So yeah, this is the steps that we have to see for preparing a particular IC. So I hope you are all clear with the VLSI design flow. It is also very important one. So we'll see the next topic, that is nothing but your stick diagrams. That is very important. Everything is important in VLSI. So in the next topic, in the next class, we are going to see your stick diagrams. For today's class, I'll end the class here itself. If you are having any doubts, please do let me know. Give the attendance properly. Okay, thank you.